11.1 Systems of Linear Equations in Two Variables. Part 1 Solving Systems Graphically. Southwestern College, Professor Maria Olivas. Solving systems of linear equations in two variables. Objectives. Solve systems of linear equations in two variables graphically. Solve systems of linear equations in two variables algebraically by substitution and elimination. Use the graphing calculator to analyze systems. Solve applications involving systems of equations. A system of equations in two variables consists of two or more equations considered simultaneously. For example, y equals 2x minus 5 and y equals x minus 1. A solution to a system of equations consists of all ordered pairs x, y that satisfy all equations, that is, make all of the equations true. When solving systems of linear equations in two variables, there are three methods we will be using in this section to find the solution. Number 1, the graphing method. Number 2, the substitution method. And number 3, the elimination method, or also known as linear combinations. Solving systems graphically. One way to find the solution to a system is to graph each equation and find any points of intersection. For example, solve the system by graphing y equals 2x minus 5, y equals x minus 1. I am going to write out what slope-intercept form is. So slope-intercept form is y equals mx plus b. Both of these equations in this system are already written in slope-intercept form. Y equals 2x minus 5, our y-intercept would be 0, negative 5. And our slope would be 2. Which could be written as 2 over 1. That way you know to go up 2 units and to the right 1 unit when you're going from one point to another on this line. For our second equation, y equals x minus 1, we can also see that this is in slope-intercept form. Our y-intercept for this equation is going to be 0, negative 1. And our slope for this equation is 1, which can be written as 1 over 1, which means we will be going up 1 unit and to the right 1 unit when we go from one point to the next to help us find another point. I'm going to label our axes. Our vertical axis is the y-axis and our horizontal axis is going to be the x-axis. Here we have a coordinate plane with the x-axis labeled from negative 5 to 5 by a scale of 1 and the y-axis labeled from negative 5 to 5 by a scale of 1. We will start off by plotting our line for our first equation, y equals 2x minus 5. We will start with the y-intercept. So if we want to plot that y-intercept point, that will be at 0, negative 5. And I will label the ordered pair. And from that point, I will go up 2 and over 1 to the right to come up with another point on our line, which will be at 1, negative 3. And if we connect those 2 points and extend our line past those 2 points, then that will give us the line y equals 2x minus 5. Our second equation, we're going to start off with our y-intercept at 0, negative 1. I will label that ordered pair 0, negative 1. I will come up with another point by using the slope. I will go up 1 unit and 1 unit to the right from the y-intercept, which will land me on the point 1, 0. I will connect those 2 points and extend my line. and then I will look for the point of intersection. Recall that when we graph a system of two linear equations, the point at which the two graphs intersect is a solution for both equations and therefore a solution for the system. I'm also going to label the equations of those lines right above them. So it appears that the solution for this system is going to be right here at 1, 2, 3, 4. It looks like 4 for the x coordinate and 1, 2, 3, 3 for the y coordinate. So it will be at 4, 3. This represents our solution to our system. Now, in order to verify that this truly is a solution, since we did do this using the graphing method, we should check our solution by substituting it back into both equations. We do need to make sure it satisfies both equations. Let's start off with the first equation. Our first equation, we're going to substitute that 4, 3. We're going to substitute 4 for x and 3 for y. And we're substituting into y equals 2x minus 5. So 3 equals 2 times 4 minus 5. 3 equals 8 minus 5. 3 is equal to 3, which is a true statement. That means it satisfies the original equation. Our next equation is y equals x minus 1. So that'll be 3 equals 4 minus 1, which is 3 equals 3. That is a true statement, therefore it satisfies our second equation, and therefore we can say it satisfies the system. It is a solution to the system. So we can write out the solution is 4, 3, and we can box that solution in. Next, we are going to verify this on our graphing calculator. And we are also going to write down the steps that we're going to take on the graphing calculator right here so that we don't forget them. So let's go ahead and take out our graphing calculators, and we are going to first turn them on, and then we're going to press the Y equals button. The Y equals button is going to be in the upper left-hand corner of your graphing calculator. Once you press that in, you're going to be typing in the equations that we want to graph. So type in your equations. For the first one, you're going to go where it says backslash y sub 1 equals, and then you will type in 2x minus 5. And then you press down and then backslash y sub 2 equals, and you will type in x minus 1. And then you will press the button that says graph in the upper right-hand corner of your graphing calculator. Now you do want to make sure that the point of intersection appears on your screen. If it doesn't, it is important to adjust those window settings. Next, we are going to hit second, and then you are going to hit the trace button, but we want the command that's above the trace button, the calculate command. So you're going to hit trace, but it's because you want that CALC command above the trace button. Once you hit that, you're going to be taken to another screen. And you're going to want to hit number 5, intersect. In order to hit that command, you will either press the number 5 button on your graphing calculator, or another option is you can press the down button 4 times. So right now when you're looking at your screen, it should have like the cursor on the number 1 where it says value, and if you press down 4 times, you'll go 1, 2, 3, 4. It should land you directly above the number 5, right next to the word intersect. Once you have pressed that down button 4 times and landed exactly on that number 5, then you can press the enter key. Once you have done that, you should be placed on the graphing screen. You should see your two lines intersecting. It should be asking you first curve with a question mark. And you should be on either one of the two lines, the cursor button. You're going to press enter. Second curve, you should have the cursor button on one of the other lines, on the other line, and then press enter again. And then when it says guess with a question mark, you're going to press enter one more time. So a quick way to get through this is just press enter 3 times, and it should get you through this part pretty quickly. After you do that, it should provide you with the solution. It should say intersection x equals 4 and y equals 3. Now, when we write our answer, we do not want to write it this way. We want to write our answer or our solution as an ordered pair. So we're going to rewrite this in the form of an ordered pair. So write solution as an ordered pair. So we're going to open up a set of parentheses, and then we're going to write 4, 3 and close our parentheses, and then box in our solution, and that's it. Now we're going to show this what it would actually look like on your graphing calculator, now that we've written out all the steps to do this process. So this is what you should be seeing on your screen when you go to your graphing calculator. We're going to press the Y equals button first. And then it's going to have that backslash y sub 1 equals. We're going to type in that 2x minus 5. And then we're going to press down to write our second equation to get to that backslash y sub 2 equals. And we will type in x minus 1. And then we will press the graph button. And you should have something that looks like this. Now I'm noticing that my window is not in the standard view, so I'm going to go over to the zoom button and I'm going to press number 6 for standard. And so I can get that standard window. So hopefully all of our windows look the same now. I want the point of intersection between these two lines. So I'm going to press the second button and then I'm going to hit the trace button. And I want number 5 for intersect. So I'm going to press 5. First curve, I'm on that line, so yes, enter. Second curve, I'm on the other line, enter, guess. And then it should give you the intersection after you've pressed enter 3 times. X equals 4, Y equals 3, and that's exactly what we were able to get before when we were able to graph our 2 lines and find that point of intersection. Next, we're going to be looking at different types of systems. So depending on the system and the number of solutions that system has, we sometimes refer to it in a specific way. So number 1, a consistent system and equations are independent. If the 2 lines intersect, we say the system is consistent and that the equations are independent. There is one solution to the system. So let me go ahead and draw a picture here so you have a visual to refer to when looking at this example. We're going to draw two lines, and these 2 lines are going to intersect at one point. That one point I'm going to label here as a general solution x comma y. It has one solution. So this, once again, we refer to this as a consistent system. And the equations are independent. When you have this type of system, you're going to notice that these lines have different slopes. And that's always going to be the case in this example, because otherwise there's no way for them to intersect and have that one solution, right? And the last piece here, there is only one solution. And that solution is represented as an ordered pair. So the word consistent means it has at least one solution, but when we say the equations are independent, then we know they're going to be two definitely different lines with different slopes, and that the most that they can have is just one solution. So we're just going to have one solution in this case, and we're going to represent that as an ordered pair. Number 2, inconsistent system and equations are independent. If the two lines do not intersect, that is, they are parallel, and let me go ahead and write down that word, parallel, then we say the system is inconsistent and the equations are independent. There are no solutions to the system. Let's go ahead and draw a picture for this. So for our visual, we're going to draw two parallel lines. Parallel lines never intersect. Therefore, there is no solution. So just to reiterate, we call this an inconsistent system. And the equations are independent. Now for this particular solution, even though the equations are independent, the slopes here are the same for these lines because they never intersect. So these lines must have the same slope. But the y-intercepts of these lines must be different. And in terms of the solution for this one, there is no solution. And when we're writing this out, you are allowed to write this out in the words, using the words no solution, or you can also represent this by writing out the empty set. The empty set may be represented, it looks like a 0 with a slash through it, or an empty set of braces. So there are 3 ways we could actually write out, right, this solution, which means there's no solution. All right, number 3. Number 3 here is consistent system and equations are dependent. If the lines actually land directly on top of each other, that is, if they are really the same line, then we say the system is consistent. But the equations are dependent. There are an infinite number of solutions to the system. The line itself is the solution set. So for the picture on this one, I attempted to draw a line on top of another line. I hope that's clear for you to see. So on the XY coordinate plane, I drew a thicker line, and then on top of that line, I tried to draw a thinner line that was lighter in color, so it would stand out that it looks like it's a line on top of another line. But they are technically the same width. One isn't really thicker than the other. I just wanted to make that emphasis. So we call this a consistent system, and the equations are dependent. If this is really the same line, then when you're looking at the equations of this, you're going to need to have the exact same slope and the exact same y-intercept. So that's what it means. So if this is really the same line, then it must have the same slope and the same y-intercept. And in terms of the solution, this is going to have infinitely many solutions. Since you do have one line directly landing on top of another line, they are going to share infinitely many points in common. They're going to intersect at infinitely many points. So therefore, there are infinitely many solutions. Now the question here is, how would we write the solution set for this? So to be very specific in writing the solution set, we're going to have to either write this solution set in set builder notation or as a parametric representation of the solution set. Because once again, what we're looking at here is we're looking at all of the points that the system has in the solution set, which is all the points these lines have in common. They have infinitely many points in common, all the points that actually land right on top of the line. So the solution is all of the points on this line. So let's go ahead and write that solution set. Why don't we start off by writing the solution set first in set builder notation. First off, we need to know the equation of this line if we want to do that. Let's give this line the equation y equals -1/2 x plus 3. I think that's pretty close. It looks like that would work for this line. So let's say that the equation for this line is y equals negative 1/2 x plus 3. So we would open up a set of braces and we would say it's going to be the set of all ordered pairs x comma y such that y equals 1/2 x plus 3. Close your braces. And this would represent the solution set in set builder notation. Or if we wanted to write the parametric representation of a solution set, we would say it's going to be x comma, and then we would write here 1/2 x plus 3 because this is the value, this is what y is equal to in terms of x. Either one of these representations would satisfy for writing down the solution set for this particular system if we were asked to solve a system like this. All right, let's go ahead and start doing some examples. Let's solve each system by graphing the pairs of lines and finding the point of intersection. Also, state whether the system is consistent or inconsistent and whether the equations are independent or dependent. Let's begin by rewriting these equations in slope-intercept form. Let's start off with 3x minus 2y equals negative 14. So in order to isolate the y, I'm going to subtract 3x from both sides of the equation. These are going to add up to 0 here, so that would just leave me with a negative 2y equals negative 3x minus 14. I'm going to divide both sides by negative 2, which leaves me with y equals a negative 3 divided by negative 2x minus 14 divided by negative 2. And then if I simplify this, y equals 3/2 x plus 7. So this equation is now in slope-intercept form. That's y equals mx plus b. So the y-intercept would be 0, 7. And the slope is going to be 3/2. So that means I'm going to be able to go up 3 units and over 2 units to the right. But notice how my y-intercept point is very high up here in my graph, and I really don't have any more space to go up and to the right based off of how this graph is. So I can rewrite 3/2 as negative 3 over negative 2. And this means I can also go down 3 units and to the left 2 units from my y-intercept. And I do have space to go down. So that's what I'm going to do. So that's going to land me right here. If I go down 3 units and then over 2 units to the left, I will be at negative 2, 4. So I'm going to go ahead and also label my y-intercept 0, 7 and draw my line that extends through both of those points. So this is the line that represents that equation, that 3x minus 2y equals negative 14, or the way I wrote it, y equals 3/2 x plus 7. Now to rewrite the second equation in slope-intercept form, I'm going to subtract x from both sides of that x plus 4y equals 0 equation. And that will leave me with 4y equals negative x, divide both sides by 4, and now I'm going to be left with y equals, we could write that as a negative 1/4 x. So this is now in slope-intercept form. I'm actually going to rewrite it so you can actually see the y-coordinate of the y-intercept, which is going to be 0, plus 0. You don't have to do this, but I'm just doing it so everyone can be very clear what the y-intercept is. The y-intercept is going to be at 0, 0, and the slope of this line is negative 1/4. And once again, you could put that negative in the numerator, you could put that negative in the denominator. If you put it in the numerator, then we're going to go down 1 unit and then 4 units to the right. And if you wanted to switch it around, you could also do that so that you could go instead up 1 unit and then 4 units to the left. Either way will give you the same slope. All right. Okay, so we're going to start off by plotting the y-intercept at 0, 0. And now we need another point. I think I'm going to use the up 1 unit and the 4 units to the left. So we're going to use the +1 over the -4 slope. So we're going to go up 1 unit and 4 units to the left. That's going to land me at -4, 1. And it looks like that just happens to be the point of intersection between the two lines. So that is also going to represent the solution to the system. I'm going to label each one of these lines with the equation. So first the 3x minus 2y equals -14. And then I'm going to label the other one, which was the x plus 4y equals 0. And you could use the standard form of the equation or the slope-intercept form to label those lines. Either one is fine. Next, we're going to check and make sure that that actually is the solution to our system, because we did mention how when we use the graphing method, that sometimes it might not be clear if that is the solution, and it might be nice to just check it. So I'm going to use substitution. So if we substitute that -4 into our first equation, that 3x minus 2y equals -14, it checks out. We get -14 equals -14, and that's a true statement. Now we're going to check it in the second equation, which is the x plus 4y equals 0. So we get -4 plus 4 times 1 equals 0. And -4 plus 4 is equal to 0. So 0 equals 0. Yes, it's another true statement. So I am positive that that is the solution to the system. I'm going to box that in, that -4, 1. And now we need to state whether the system is consistent or inconsistent. And we also need to state whether the equations are independent or dependent. Well, this has a solution. So anytime that your system does have at least one solution, we say it is a consistent system. And in this case, it's 2 different lines. So we're going to say, and the equations are independent. And we're going to box that in as well. All right, so that was our first problem. Let's go to our number 2 problem. So our number 2 problem, our system is going to be 3x minus y equals -4 and -6x plus 3y equals -4. Once again, I'm going to rewrite these in slope-intercept form because it is helpful when you rewrite these equations in slope-intercept form, because right away you'll be able to tell whether the lines have the same slope. They might have the same slope and the same y-intercept, which in that case it might mean that they're the same line. It's quick to identify what type of system we're going to have. So starting with the 3x minus y equals -4, I'm going to subtract 3x from both sides of the equation. So the 3x minus 3x zeroes out, and we're left with -y equals -3x minus 4. We're going to divide both sides by -1. So y equals 3x plus 4. So my y-intercept in this case is going to be 0, 4, and my slope is going to be 3. But I'm going to rewrite that as 3 over 1. That way I know I'm going to go up 3 units and 1 unit to the right from my y-intercept to get my second point on my line. So let's go ahead and go to 4 on the y-axis. And I'm going to go ahead and draw a point there. 0, 4, And I'm going to go up 3 units from 0, 4, and then 1 unit to the right, and that's going to land me on the point 1, 7. Now that I have 2 points, I'm just going to go ahead and connect those 2 points and extend my line past those points. And there we have our first line. Now we're going to move on to our second equation. Negative 6x plus 2y equals negative 4. And I'm going to add 6x to both sides of my equation. The negative 6x and the positive 6x are going to zero out, and we are going to be left with 2y equals 6x minus 4. Now we can divide both sides by 2, and the 2's we're going to divide out. Just give me 1y equals 3x minus 2. Now this is in slope-intercept form. By looking at this, I can tell that we have the exact same slope in both of our equations. The y-intercepts are different though. This y-intercept is at 0, negative 2. Therefore, that tells me that these two lines are parallel. And the slope is 3, just like my first equation. And I'm going to rewrite that as 3 over 1, just to remind myself to go up 3 units and to the right 1 unit. I also want to point out at this time how we have the same slope in both of these lines. And since I have the same slope and different y-intercepts, that means that these lines are parallel. I want to emphasize the importance of having different y-intercepts. All right, in order for the lines to be parallel, you have to have the same slope, but different y-intercepts. All right, so let's go ahead and plot our y-intercept for our second line, which was at 0, negative 2. And from there, we're going to move up 3 units and over 1 to the right. So that's going to land at 1, 1. And if I connect those 2 points and extend my line, there is my second line. So yes, these lines, I can see that they are parallel to one another. Now we need to go ahead and label these lines. I'm going to label the first equation, y equals 3x plus 4, for the first line that I drew. And the second equation, y equals 3x minus 2. And once again, I had mentioned earlier, it's okay if you use the equations that are in slope-intercept form or the ones that are in standard form. Either ones are fine. Now, since these are parallel lines, there is no solution to this system. So you can write out the words no solution, or you can write out the empty set. Either one of those would be fine. And the reason there's no solution is because there is no point of intersection between these lines. These lines will never intersect. Now, one thing you never ever want to do is you don't want to write the empty set within the empty set. Okay, that's a big no. You don't want to do that. You just want to write out one of those versions of the empty set, and that's enough. Okay, let's talk about what type of system this is. So this system, since it has no solution, we're going to call this an inconsistent system. And these equations are independent. All right, we're ready to move on to problem number 3. We've got y equals negative x over 3 minus 2. And negative 2x minus 6y equals 12. First thing I'm going to do is I'm going to rewrite that first equation. I want to rewrite it so that you can clearly see what the slope is. We're going to rewrite that as y equals negative 1/3 x minus 2. Therefore, it's easy to see that our y-intercept is going to be 0, -2, and our slope is -1/3. You could put the negative on the 1, or you could put the negative on the 3. If you put the negative on the 1, we're going to be going down 1 and over 3 to the right. Okay, now we're ready to rewrite the second equation, the -2x minus 6y equals 12 in slope-intercept form. So we're going to add 2x to both sides of the equation. The -2x and the +2x, they will add up to 0. And we have -6y equals 2x plus 12. We're going to divide both sides by -6. The -6's will divide out on the left, and we're left with y equals -1/3 x minus 2. So looking at this equation, I can see that the y-intercept is going to be 0, -2, and the slope is going to be -1/3, which is exactly the same thing I got from my first equation. So I will be going down 1 and to the right 3. Actually, looking at the two equations in slope-intercept form from both equations, I can see they're both exactly the same, so I can tell that I'm drawing the exact same line for both of these. So we're just going to draw one line. So let's go ahead and start graphing that. We're going to begin with the y-intercept. So here we're going to go on the y-axis to 0, -2. I'm going to plot my point there. I'm going to go down 1 unit and 3 units to the right, and that's going to land right on top of the point. 3, -3. I'm going to connect those 2 points and extend my line, and there is my graph. So all the points on this line represent the solution to my system. So if you remember, I think we mentioned how to write this before. We can first, let's label our line. We're going to label it with the equation y equals -1/3 x minus 2. And then when we write down our solution set, we can write down our solution in set builder notation. So in that case, we're going to open up a set of braces, and then we're going to say the set of all ordered pairs x, y such that this satisfies the equation y equals -1/3 x minus 2. And we could have used the original equation that was given to us or the one that was in standard form. They all represent the exact same equation, so they all would have been fine. Either one of those versions would have represented the same equation. I'll write down the other way I could have written this down. I could have used the equation that was in standard form. So the set of all ordered pairs x, y such that it satisfies the equation -2x minus 6y equals 12. Or another way that I can write it in what we would say is the parametric.
All right, well, let's go ahead and box in those answers.
X,
so I'm going to box in
and
all
then I
three
will
of
write down what
these
y has to be
different,
equal to. Y has to equal -1/3 x minus 2.
I'm also going to write in here that this is a consistent system and the equations are dependent. And I'm going to box that in as well. And that's it. We're going to be done with that problem now.